elements or unconnected lines in the network, which include the transformers also. So that is the primitive bus matrix or bus admittance matrix. So what we are now going to do is a Z bus. Z bus mainly used for the short circuit studies. You know, the short circuit study is mainly done to find out what are the fault currents for various type of faults, and knowing that fault current, you can have the protective devices in the system so that you can avoid major damages. That is the idea of doing these short circuit studies, which we call as the transmission line, sometimes alone or sometimes connected in series with the transformers. It is an element. The element can be classified into a branch or link. Branch or link. A branch will always give a node or bus in addition to the partial network, and a link will not give a new bus or new node. So that, of course, many of you know that, and we are now going to see how, when the element is a branch, how it is you are going to develop the impedance matrix, the bus impedance matrix. So taking the system parameters and coded bus numbers, you are going to develop the bus impedance matrix. The performance equation of the partial network, it is given by E bus equal to Z bus into I bus. Just like the Ohm's law, E equal to Z into I. It is not for the individual element, it is for the network. So E bus, it is a vector of M by 1. M by 1, that means a column bus matrix, or it is a column matrix, you can say voltage column matrix consisting of, suppose the partial network contains M buses, so it is a M by 1 vector. It is a M by 1 column vector. And Z bus is a M by M square matrix. And I bus is again a column matrix M by 1. M number of elements, M number of bus currents, and of course you have another bus, what is called the reference bus. Reference bus or ground bus. This figure indicates it's a partial network. M1 to M number of nodes, and 0 representing your reference node. So these voltages are measured with respect to the reference to the respective buses. 1, 2, like that, M number of buses. That is your E bus. And O is your reference bus. So that is the indication of how you are going to, before the addition of an element, whether it is a branch or a link, you are going to have this as a reference partial network. Now, of course, when PQ, that is the added element, is a branch, a new bus Q is added to the partial network, and thereby the dimension of the matrix is now increased by M plus 1 by M plus 1. That is, the size of the matrix will be increasing. And of course, M plus 1 by 1, that is what? The current vector and the voltage vector, it is a M by. Then if it is a link, then there is no addition of the branch, the addition of the node, and therefore it is in between the existing buses, and therefore no new nodes or buses. So the A indicate element PQ is a branch, and P indicate element PQ is a link. and this is the addition of a branch, addition of a link. So now, how we are going to find out, because there is no new, there is a new bus in the partial network when the element is a branch. So addition of a branch, that is the topic. E1 to EM, that is the existing partial network elements, and EQ, that is the newly added the element EQ, and of course you have Z11, Z12 up to Z1M, Z1M, and then the column wise it is 2-1 and up to M1. These are M by M, that is your existing. This is a old the matrix without the addition of the element. Now we have to find out what is the elements in the last the column and the last row. And the currents are I1 to IM, and IQ is the current in the qth bus. Now ZQI equal to ZIQ. That means it is a partial network, passive, all the elements are passive, and therefore it is a bilateral network having the mutual admittances are equal. Therefore ZQI equal to ZIQ. I varies from 1 to M, and the element branch PQ is a element added. So is E1 equal to Z1I into II. So E1 is calculated by multiplying Z1I into II. You are injecting current in the ith bus by 1 per unit. 1 per unit. So it is E2 equal to Z2I into II, like that up to EM, and EQ equal to ZQI into II. So that is the calculated elements of the bus voltage vector. P and Q, the added element is that. So voltage across PQ will be, that is your VPQ. So EQ equal to EP minus VPQ. Now the currents in the elements of the network, IPQ, that is the current in the PQ element, and here YPQ, PQ, YPQ rho sigma, this is your the self admittance, self primitive admittance of the element PQ. And YPQ rho sigma is a variable mutual the admittance matrix. PQ with respect to PQ rho sigma varies from the other elements in the partial network. VPQ and Y rho sigma VPQ, because it is a symmetrical matrix. Rho sigma and V rho sigma. Just like the VPQ, V rho sigma is also the voltage drop off or voltage difference between roth bus and sigma bus. So that is the other representations. IPQ, VPQ, current through voltage across the added element PQ. I rho sigma, V rho sigma, current and voltage vectors elements of the partial network, which are the except PQ, the other elements in the partial network. Then YPQ, PQ, self-admittance of the added element, and YPQ, rho sigma, mutual admittance between added element PQ and the elements rho sigma. and of course this is the transpose of the vector ypq rho sigma. Y rho sigma is the primitive admitted matrix of the partial network because except pq, the other elements in the network. Take some time. Currently the added branch IP, because it is not a closed element, but P and Q both are open. IPQ equal to 0. Current through the branch IPQ equal to 0. And V rho sigma, that is given by V rho sigma, E rho minus E sigma. That is the voltage drop in the rho bus and sigma bus. Then IPQ, according to that matrix, just we have shown a 2 by 2 matrix. IPQ equal to 0. So when you multiply the first row and the column, YPQ was the first element in that 2 by 2 matrix, and VPQ and YPQ rho sigma V sigma. Though it looks like a 2 by 2, only one element is the self admittance. The other elements are the other elements in the path. Then therefore now VPQ is taken out from this equation. VPQ equal to this element product of these two divided by YPQ PQ. YPQ PQ, therefore VPQ. Now combining this VPQ equal to YPQ rho sigma, in the place of V rho sigma, you are taking a rho and the sigma divided by YPQ PQ. And EQ equal to EP plus this one, that is VPQ. EQ equal to EP minus VPQ. So this is substituted here so that you get this equation. Now when IA equal to 1, using that, what you have seen in the first is the second equation, we can now have ZQI equal to ZPI because IA equal to 1. ZQI into IA equal to EQ. So that is now written in this form. So this is all the mutual elements of the partial network. Mutual elements. ZQI equal to ZPI, O sigma, this one, where I is not equal to Q. So you have to find out the element ZQQ separately. That is the diagonal element have to be found separately, and that is the next thing. ZQQ can be calculated by injecting a current at the Qth bus. So E1 equal to Z1QIQ, the same set of equations as you have seen earlier, and IQ equal to 1 per unit, and therefore you have IPQ. IPQ is the current through the PQ branch, and I in the Q, the current IQ equal to 1 per unit is injected, and therefore you have IPQ plus IQ equal to 0, or you can take this minus IQ, IPQ equal to minus IQ, that is equal to minus 1. So this the equation we are going to use the next, that is IPQ equal to this equation already we have seen minus 1, and therefore VPQ equal to this also we have seen earlier. Now combining this to we get this equation. That is what VPQ. What is our idea is now to get the diagonal element ZQQ. So ZQQ equal to ZPQ. That is IQ is made equal to 1 as we have done earlier for the mutual elements. Now the diagonal element will be ZQQ, YPQ. That is ZPQ 1 plus this equation divided by this, and therefore the diagonal element is given by equation 4212. 4212. So we have first determined the half diagonal elements or mutual elements. Now it is a diagonal element. So all the elements are now determined. Now suppose instead of the reference node 0, if Q is made, if there is no mutual coupling between the added branch and the other elements of the network, then the elements YPQ rho sigma will be 0. There is no mutual coupling between the other elements and YPQ, and therefore you can see that this ZPQ PQ will be 1 by ZPQ only, right? Because there is no mutual coupling. And ZQI equal to ZPI. ZQI equal to ZPI because the other elements are equal to 0. And ZQQ equal to ZPQ plus YPQ, and that is for the diagonal element. So for half diagonal element only no mutual coupling. Therefore you get this one. Now further, if Q is made reference node instead of O, then what will happen? P is the reference node. Then Pi, that is what, equal to 0. I varies from 1 to m. I is not equal to 2. Similarly, ZQI equal to 0, and therefore ZPQ equal to 0. And therefore you have the diagonal element equal to ZPQ itself. That is only because of that diagonal element alone, qth element alone. So that is for the addition of the element when it is a branch, the off diagonal elements and diagonal elements are determined in this manner. So because it involves some the calculations and all, normally it looks something difficult, but when you follow uniformly, you can see that it is just like a circuit the analysis. You can do it very fast. Now the addition of the element is a link. A link means between the existing network, existing nodes, you are going to have the element. So that is the link. So here you can see that E1 to EM, existing partial network, and Z11 to Z1L and ZM1 to ZML. That L is the fixtures node. You are going to add between the L and Q. You have P, L and Q. Okay. So of course that network you can see, this is the partial network. You can see that 1 to I and P and L is the fixtures node and Q is the node and O reference as we have seen earlier. So this EL is so selected such that the current through this element equal to 0. And IPQ equal to 0. Then you can see that inject a current from the reference node II 1 per unit to the ith bus. Thereby you can determine the off diagonal elements of the network and the diagonal elements of the network also by injecting current I equal to 1 per unit in the qth node or qth bus. So EL up to E1 to EM existing buses, and EL is a fixtures node. So this fixtures node you are going to eliminate so that when element is added is a link. there is no dimension of the matrix remains same. It is not changing. So you are going to have m by m, that is the dimension of the matrix, and EL, this row and this column, you are going to eliminate it. Eliminate this EL row and the column, the 1 to L, 1 to IL, I1 to IL, you are going to eliminate. So that means the existing elements Z11 to ZML, all the elements get modified. Now it is not the same as the Gaussian network, just like a branch. Here all the elements get modified. So how we are going to get the modification? For the mutual elements as well as the diagonal elements. So EL, that is the value of the source connected to the L2 node. That is what EL. EL equal to EL minus EQ. The difference between EL, no voltage at the L2 node and the Q2 node, EL. So now, as you have done for the branch, you can do it for the EI equal to ZLI II, where K varies from 1 to M, and EL equal to ZLI into IA. Now putting II equal to 1, injecting a current 1 per unit in the I2 bus, you have the elements, all the voltage elements, and EL equal to EP minus EQ, and the voltage drop in that EPL. Now, as the EL is selected so that the voltage through that element equal to 0, now IPQ equal to 0. So this is based on that is the policy in this. You are going to make that EL equal to such that the current through the IPQ equal to 0. Now IPL from P to L equal to multiplication of this YPQ VPL, YPLQ and UPQ. This equation as you have seen in the previous element. So IPL, IPQ equal to 0, therefore VPL equal to this, and VPL rho sigma equal to YPQ rho sigma, and VPL equal to PL equal to Q itself, therefore the self-admittance of the PL equal to self-admittance of the PQ element itself, and VPL equal to this separating from the LA equation, then have this VPL, and substitute in the EL equal to EP minus that equation, you get ZLI equal to ZPI, because IA equal to 1 per unit, except I equal to L, not equal to I, not equal to L. The other elements you can determine using this equation. That is what the corresponding off-diagonal elements. And EK equal to ZKL into IK varies from 1 to M, EL equal to ZLL into IL. Now let IL equal to 1 per unit. You can calculate what is the ZLL. So, ZLL equal to ZPL minus Z, sorry, yes. So similar, the analysis, if there is no mutual coupling, what will happen? If Q is a reference node, what will happen? So all these things, as you have seen in the branch type, you get this. Then the elements in the Lth row at the column of the precedence matrix, Gaussian network are found from equation this. So now you can see that Z bus equal to Z bus I bus, Z IL into IL. So this is for the new
this element is new. This of course one Z bus is the I bus existing partial network, and EL equal to ZLJ I bus into ZLL IL. So from this you are going to eliminate EL. EL is going to be eliminated. So now Z bus equal to Z bus ZIL LJ ZL into I bus. So you can see that Z bus equal to Z bus E bus equal to Z bus into I bus. That is the existing partial network, and this element minus this one because of the addition of the link. So you have to or you can say that the new impedance matrix equal to within bracket Z bus minus ZIL LJ divided by ZIL. So Z bus modified, that is your new Z bus matrix equal to Z bus before elimination, that is the existing partial network, minus the product of ZIL LJ divided by ZIL. So this is your the final. So you get whether it is an element, is a branch, or the element is a link. You can always find out all the elements. That is using this equation you can find out. So knowing this bus admittance matrix, you can straight away use that in the short circuit calculations, how the fault current can be determined. That is the idea. So the power system analysis mainly focuses with the load flow analysis first, and then the short circuit analysis. So load flow analysis normally we use ATYA, that is the thing. So assuming, as the professor said in the morning, the fast decoupled load flow have many assumptions, and when the network is very large, you can use that fast decoupled load flow, and you can find out the 4 parameters for each of the network, that is P, Q, V, delta. So depending on which two are the buses, the variables are known, you call that by a particular name. So that's our system analysis, we require the calculation. Once the power system analysis, when you do the load flow analysis, you know which of the buses have without overloading the power, either the power or current, or the other one you have when there is a difference between the voltage within the limit, the 0.95 and 1.05, you can do the corresponding rectifications. So that comes under the power system operation and control. So just the professor started the power balance equation. What is the power balance equation? The power balance equation is given the sum of the power generation should be equal to the power demand and losses. Power demand and losses. When there is a real power difference, what will happen? When there is a reactive power difference, what will happen? When there is a real power difference, which means it is when the real power difference is positive, that means generation is more than the load, what will happen? The frequency is going to be high. So frequency will act as a sensor. The operator will know that because the power generation is more now, so he has to reduce the power generation. So he will see the frequency sensor and get the corresponding changes. By the speed governor is that, and we can make the corresponding using the local control. We can make the frequency equal to the required operating frequency. And of course, we know what will happen when the frequency is not considered. All the electrical equipments are designed for only the particular frequency, plus or minus 1%, and voltage plus or minus 5%. So that is the required the tolerances for the electrical parameters. Just like professor started, you can compare
the pulse with the frequency and pressure with the voltage. The blood pressure with the corresponding voltage, and thereby you can analyze the power system. In what way you have to going to change that. When there is a frequency change, what do we do? When there is a voltage change again, you can do by local control or system control. The local control means you are going to excite the excitation of the generator, you are going to vary and make the voltage correspondingly usable voltage. And system control will be you are going to add the capacitor in series or parallel to the load so that you can make it is an operable voltage. You can make use of the operating voltage. So the problems in the power system normally it varies as a first one, because the load is it is not constant, it is always varying from time to time. So it is considered as a first problem is a load forecasting problem. Load forecasting problem. Then comes the unit commitment. Which are the unit you are going to commit for a given load? Though you have a number of units, which unit you are going to commit? And the next problem comes economic dispatch. The economic dispatch, considering the economic dispatch, you are going to see which are units to be committed so that it is on the total fuel cost required to be minimum. So that is the idea. The load forecasting problem, the first problem itself, you can see that how you are going to make it as whether it is a long-term problem or it is a mid-term problem or a short-term problem. So which one you are going to solve? Suppose the lead time, that is the forecasting interval, is a long, say about or 1 year, then you can use for the extrapolation techniques. What you are going to have, you know that the extrapolation techniques will be straight line method is that, parabola method is that, it is a second order equation method, or exponential curve method. So these three methods you can use it depending on the data. Of course, one particular method is not, you cannot say that it is suitable for only this type of load and digital method. You have to use it all the three methods, and finally you have to judge which method will be giving the total error equal to minimum. So the total error is decided on based on the method of least square. Method of least square is nothing but the error equal to actual value minus the calculated value of the load. If you draw a XY graph representing your Y coordinate, the load, and the X coordinate, the time, whether it is a small time or long time. Normally, these methods are for long time, and therefore the X axis is a time. You can see that even if you have the data, some intermittent data, you have the load for this some 10 years back, and another load at some 7 years back, and another load at the 5 years back. Some data are missing. Even then, you can use this extrapolation technique to find out the load for the future time. That is called our load forecast. So error is calculated, which is the difference between the actual value minus the calculated value. Square it. You get an equation in terms of, suppose it is a straight line method, then you get A0, we make some constant, plus A1 into Xi, where Xi representing for the time at the ith interval, and Yi is the load at the ith interval. So A0 and A1 are the variable. because the loads are not different values. So find out A0 and AI using the method of least to square. You know the error equation, square it, find out the total error. The total error, which is a function of both the constants A0 and A1 for the straight line. What I am talking about for a straight line. And of course it is a parabola equation. You have A0, A1 and A2, one more constant is going to come. And for exponential curve, you have C to e power some dx. So that C and D, you have to find out what are the constants of C and D, so that you can find out the corresponding constants. So total error, when you differentiate the total error with respect to A0, first dTE, dou TE by dou A0, you get an equation. And dou TE by dou A1, another equation. Because it is only two constants are there and you have two equations. So you can solve it easily. Two unknown, two equations. And therefore you can solve it easily, find out A0 and A1. And once you know A0 and A1, you can, by extrapolation method, you can find out the load at any time, maybe for the 15th year. You have the load from 6 or 7 loads are available. You are going to find out the load at from 15th year. You can find out easily by using that A0 and A1. Right. So that is the method, straight line method. Like that for parabola method, you can have three constants, A0, A1 and A2. Differentiate with respect to the constants, you get three equations. So what you are going to have is a 3 by 3 matrix. 3 by 3 matrix. Once you solve for these three constants, then you can extrapolate it and find out the corresponding. Similarly, exponential. Exponential also you have. Now, you are given a set of data. Now you apply all the three methods, straight line method, parabola method, and exponential method. You can always get the total error. If the total error for the same set of data, say gives 2000 for straight line method, 1500 for parabola method, and exponential method it gives 3000. Which method you prefer? 1500. The total error equal to 1500 is a minimum value. The policy is, or the aim of the method is least square method. That is, the total error should be minimum. So you will use the parabola method for finding out the load in the future. So that is the load forecasting for a long term. And of course we have for the short term, because load is not concerned. If you take that as a stochastic variable, then naturally you have to include the weather components and the special components. And similar method also you can use it to find out the corresponding load in the future. So that is what first once you know about the power system, networks and other things, then you can use the same analysis for the operation and control problems also. Economic, that is unit commitment, and then for the economic dispatch. All these three problems can be easily solved, which comes under operation and control. So with this overview, just you can, any doubt if you have, you can just will clarify that. Any questions, please?
So I have a question.
Yeah, please.
When would you do this linearization? When do you need rigorous nonlinear simulation?
Yeah, that is it.
What are the assumptions here?
Yeah.
To apply this?
Yeah. Now, when the data is collected data, it follows a straight line, just like for 1 year, it goes like the linear manner, you can choose that. Otherwise, suppose it is not linear, then you have to go in for the non-linear. Sometimes the load will be, one load will be here, it will not be following the linear, another one will be there. So naturally you have to follow the non-linear methods.
That will be a lot more time consuming.
Time consuming, yeah, definitely it is a time consuming method.
And people generally do only linear, mostly.
Mostly for long-term forecasting mostly.
Mostly.
Extrapolation methods. Yeah. You should ask a question, why Z bus and Y bus we are considering?